All right, and now it's time we move forward towards more AI and agentic stuff. I know a lot of Vibe coders are still with us here in the audience, and it's time that I invite on stage Andrea, who's a researcher at Horizen Labs, to talk more about building trustless on-chain AI. It's all the buzz, and Andrea's going to walk us through it. Andrea, are you ready?
Yeah.
Let's do it. All the best.
Hello, everyone. So today we are going to talk about federated learning and how verifiability can fit on top of that, and we'll see how verifiability can enable a lot of advantages in federated learning in terms of security and in terms of many other things that we are going to go through. So first of all, due mentions to my colleagues, Francesco Bruschi, Marco Esposito, and Tommaso Gagliardoni, who are colleagues both from the university and Horizen Labs. So let's start, and let's first of all take a look on motivations and on what federated learning is as a first thing. So let's say in the federated learning framework, the raw federated learning framework, we have many clients that trains a model locally on their private data. So we have the advantage that the data set to remain concealed. And these local models are then used, are then sent to an aggregator that aggregates the model, and then it redistributes it to the clients, and there is this sort of iterative procedure. This is mostly used in healthcare, in finance, and in those fields where the data set is containing sensitive information. But of course, for instance, in healthcare, so we can assume that hospitals are trusted, but now the federated learning can be used also for many other use cases and applications. So in the general case, we don't have any specific guarantee that the entities are trusted. So these works rely on that. So let's take a look quickly at the agenda. So we'll see some preliminaries on federated learning, something on verifiability. Then I'm going to explain you a framework that we built to enable verifiability on federated learning. Then we'll see the state-of-the-art solutions, and then we'll see where the research should focus. And then, of course, we will talk about future and AI agents, because, of course, it's the most hyped stuff of the moment. OK, so let's take a look, first of all, at the federated learning, at the raw federated learning. So I know that you are both technical and not technical persons, so I tried to reach out both of you. So for the technical person, focus on the procedure, and for the not technical one, focus on the image. So as I told you, it's an iterative procedure where you can see many clients that trains a model locally. Then this model is sent to an entity called the aggregator that takes these partial models, aggregate them, and redistribute them to the clients. And then if a stopping criterion is met, that's the final model that will be deployed. Otherwise, proceed with another step, with another iteration. So there are many advantages. Of course, you can obtain a better model since you use more data from many clients. So you can obtain a model that generalizes better. But this comes also with some drawbacks. For instance, the fact that there are many entities can increase the attack surface. We can find many attacks related to federated learning. There are inference attacks that are inference and gradient inversion attacks that are nicely mitigated, let's say, just by the fact of sending the weights masked in some way, so there are secure aggregation and differential privacy stuff that you can use. Then there is model poisoning that's mitigated but not so mitigated. Then we can find global model tampering, selective dropping, so the aggregator that get rid of some of the updates, and free riding, the fact that clients can just participate but without collaborating, so trying to get the model without the actual training. So smarter mitigations and mitigations for many of these attacks can come from verifiability. So indeed, verifiability can really help in mitigating certain type of attacks. So here, just a quick overview of verifiability itself. So an informal definition is that verifiability can enable the possibility to a third party of verifying the computation without the need of re-executing it completely. We can find two forms of verifiability, ZK-based and TE-based. And each one of those comes with advantages and drawbacks. For instance, ZK-based are based on cryptographic assumptions, while TE-based are based on hardware assumptions. Of course, you will certainly have heard of Snark and Starks, and for ZK, and you will have heard of Intel SGX and Intel TDX and ARM Trust Zone for TE-based. So this just to say that there are multiple ways to achieve verifiability with advantages and drawbacks. So let's take a look at the verifiable framework. There are many challenges in machine learning. Data inclusion or exclusion could be one thing that we want to prove. Provenance and authorship of the data set. And one specifically for federated learning is collaborative correctness over partitions. So verifiability can manifest on the verifiable data usage, on the training part, and on the on the aggregation side. So here, this slide, I know it's quite dense, but just to show you that we have built this framework where it's possible to make those 7 claims provable and verifiables. The most important one are data binding and training correctness that are related to the training, and AG1 and AG2 that are related to the aggregation. So just to take a quick look at the algorithm, you can commit to the data, and you can use you can essentially prove the training procedure, taking as input the committed data and getting as output an handle to this to the weights that can be they can be encrypted or they can be in clear, and we can commit and push everything on a transcript that can be, in this case, a blockchain. For the aggregation side, this algorithm can make verifiable AG1 and AG2, where simply the aggregator takes information, so the weights from the blockchain, verifies all the proofs that we call evidence, because we are generalizing, we are trying to include both ZK and quotes by TEs. So where you see an E, I'm intending an evidence. So if all the evidences are verified, so if the outcome is 1 to the verify function, then the aggregator can use this admission set and aggregate all the valid and proved weights obtaining the global model. That then will be appended on the transcript, and then it can start the next iteration, where also the client can prove the handle can verify the evidence for the aggregation. This is the state of the art. So many works are, many researchers and many universities are working on that. They are 13 papers, really recent from 2023 to 2025. So it's really at the state of the art, all of that. And this is a first slide on the comparative analysis. You can see I've divided that table between works relying on ZKP and works relying on TEs. And by the graph, you can see that the majority of the works are focusing on the aggregation part, so on AG2, so the correct aggregation. That's why that's because the aggregation are mainly linear operations that can be circuitized really well. While, for instance, you can see that on the training part, there is a lack in research because the proving scheme, the actual proving schemes are not ready because they are not how can I say? They are not so good for nonlinear operations that happen on the layers of a model being trained. Okay, then I put also the second slide on comparative analysis, showing on the first table that many works relies on the blockchain to verify proofs. Actually, 6 out of 7, and there is actually only one work relying on the TEs for the aggregation. So the blockchain can really play a crucial role for as a verification medium, but also as an auditable transcript where to record all the process. Another notable thing is that implementing verifiability on top of all of that can mitigate certain type of attacks, and that combined with privacy-preserving techniques can really we can really get a solid and sound framework. Okay, these are benchmarks, so cost analysis. Okay, so claim 1, do you remember, is the one related to data binding. So proving that I'm using certain data. That can be implemented simply with a commitment plus Merkle proof, and it's relatively cheap because, you know, a Merkle proof is cheap. And you can also see that most of the overhead comes from claim 2 and claim 3, so claims related to the training. From the fact, as I was already mentioning, that the layers are non-linear, and that's not circuit friendly, let's say. While for the aggregation, many works implement it. It absorbs most of the overhead because we have to make a weighted average of all the weights coming from certain time hundreds of parameters, but it's easy to implement in a snark because basically they are just linear operations. Okay, so where should research focus? We state that many claims that many works don't implement are feasible and easy to implement, so we really suggest to researchers to focus on that. And then, yeah, of course, focus on new proving systems to circuitize and prove all the layers of the training. We are really behind on that. And then a cool thing would be to explore this co-snark. That's a new paradigm. That's a sort of MPC where many clients can generate in a collaborative manner a proof. And this could possibly remove the aggregator. Notably, if this framework will be implemented, we will have many proofs, many evidences that are both ZK proofs and TE quotes to be verified somewhere. So how to verify them and where to verify them? Well, of course, there are layer 2s, like Optimus, Arbitrum, and Base that are already safe and cheap options when we are talking of snarks. So you can see, for instance, that for a Groth16 proof with 2 public inputs, this take fraction of cents in most of the layer 2s. But we are developing ZK Verify, that's this blockchain tailored for verifying proofs efficiently and cheaply. And you can see that for the same proof, so for a Groth16 proof that costs 220K, we can basically add another 0 in the 0.00 stuff that you see there. And you can decrease even more the price with respect to the cheapest option in the EVM environment. Okay, so to conclude, we haven't talked about agents. Let's see how our framework can be integrated also with agents. So let's frame it like that. So let's imagine a fleet of agents where each agent has two, let's say, two models. One LLM. One is an LLM, of course, to decide actions, to orchestrate the next action, so the actions of the agent, and another specified for a specific task. And the second model, of course, is the same across all the agents. And this model can be trained in a federated setting. So let's imagine different agents having different data, training a shared model. This can potentially, they can potentially achieve a better model because of this variety of data that generalizes better on the task. So we said that we are not trusting entities that are human-based, let's say. So how can we trust agent? How can agent trust each other? Well, we can rely on the VFL framework, of course. We can have two architectures. The first one is the classic with many agents acting as clients, training locally the model. And they can push stuff on the VFL medium, so to the transcript. And the aggregating agent can fetch stuff from the transcript, verifying correctness of the training, performing the aggregation, and push stuff on the transcript. So the exact same thing that we have seen before, but agent-based. And there are no difference, basically. The second architecture, we can get rid of the aggregator, and this becomes sort of a peer-to-peer or how was it called? Gossip-based verifiable federated learning, where all the agents push stuff and fetch stuff from the medium, so from the transcript, and they verify the actions that they perform each other. And at the end, they can agree on the aggregated model with a checkpoint, with a sort of, let's say, with a sort of consensus. And then if the final model and the final I mean, if the expected model with the expected characteristic has been reached, that's the final model, or they can repeat and go on with another iteration, exactly how the federated learning framework works. So that is, to wrap up, how in future clients can use the federated learning framework to improve themselves for common tasks. Okay, so this concludes my talks. This is my talk. So thank you for your attention. If you want to connect with me, you find my LinkedIn, Telegram, and whatever on that QR code. And that's the preprint of a paper that we recently made, where I've taken most of the content that I showed you. So thank you for your attention.